Okay, in this last alcohol video, we're going to look at some special reactions that are unique to 1,2-diols. We're going to look at the reactions of sulfur analogs of alcohols, thiols, and we're going to look at some of the spectral nuances of alcohols. Okay? All right, so first let's look at this reaction here. This is called 1,2-diol cleavage. It's only the second reaction we've had that cleaves a carbon-carbon bond, the first one being ozonolysis. Okay? All right, so if we take a 1,2-diol like you see here, all right, and we treat it with this molecule, periodic acid, or sometimes you're just going to see it sodium periodate and something acidic added to the solution. We're going to first make this, hypervalent iodine type ester derivative that you see right here. And this is going to cleave to give you iodine in a lower oxidation state. But most importantly, it's going to cleave the carbon-carbon bond right here. Okay, so this bond, the bond that was between the two alcohol groups, that's going to go as a result of the diol cleavage reaction. And we can think of it as basically just like this set of arrows right here, all right? Okay, and we're changing the oxidation state at iodine. Okay, we're really converting iodine from, iodine 7 to iodine 5. Okay, all right, and in the process, we get 2 aldehyde units. All right, so let's look at some of the possible products that we could get from this reaction. All right, so right here, if we were to take this compound, what we would see is that we would cleave that bond right there, and that each of these carbon-oxygen single bonds would become carbon-oxygen double bonds, okay, like you see here. And the bond between them is gone. All right, so that's the result of the diol cleavage reaction. All right, so if it's a cyclic 1,2-diol, we're also going to do a similar thing. We're going to cleave that. Each of those CO single bonds is going to become a CO double bond. But since they are also connected in 2 different ways, they're instead of getting 2 different aldehydes or 2 different ketones, we're going to get one molecule that has 2 carbonyl groups in it. If you did this reaction here, you would also notice that the cis isomer would undergo this reaction much faster than the trans, and this is because it's much easier to form a ring system, this 5-membered ring system that you see up here. This ring system will be much easier to form if the alcohols are closer to each other than and that's the case in the cis isomer, whereas in the trans isomer they're a little bit further apart. All right, in this last reaction here, we can take the osmium tetraoxide reaction and couple it with the sodium periodate reaction and generate basically what's an alternative to the ozonolysis reaction. You find that this reaction is used quite frequently by people. If you want to use ozone, you have to have a special ozone generator. A lot of people don't have that appliance, and this is a good alternative way to do that. This sodium periodate also serves as the reoxidant for the osmium tetraoxide. So you actually use quite a lot of this periodate reagent when you do this reaction. And the reaction equation is exactly the same as the ozonolysis. Okay, we cleave the carbon-carbon double bond like that, and each of the carbons becomes a C double bond O. Okay, and what you see here again is you have this piece over here and this other piece right here. So it's exactly like the ozonolysis reaction. All right, here's another reaction that's unique to the 1,2-diol system. If you're looking for it in the textbook, it's after the chapter. It's a special topic, but this is called the Pinacol rearrangement. All right? And what happens here is if you take a 1,2 diol, that's where both of the alcohols are tertiary alcohols. In some cases, that requirement isn't always held there, but it works much better if both of the alcohols are tertiary alcohols, as you'll see. You'll see why in just a second. The reaction of this type of 1,2 diol with a strong acid like sulfuric acid results in a process where one of the methyl groups, we'll just say this one hypothetically, is now bound to the other carbon. Okay, so we call it a rearrangement reaction because the carbon skeleton has changed as a result of this reaction. If we look at the mechanism, it starts out like other reactions between alcohols and sulfuric acid, like dehydration and ether formation. We're going to protonate the alcohol to form the protonated alcohol. We lose water to make the carbocation. And what happens in this case, because of the presence of this oxygen right here, we move the methyl group, okay? This carbocation here, of course, is resonance stabilized. Okay, it's a very stable type of carbocation because you can invoke the oxygen lone pair like here. And when you do that, what you see is you already have the C double bond O that you need to make in the beginning. Okay, and after losing this extra hydrogen right here, we end up with a product. All right. You don't always show it, it's not always shown that way. Sometimes we just show a concerted process where the C double bond O forms along with the carbon migrating. Okay? All right, so that's an alternate way to show it just in a single step like you see right there. Okay, all right. So let's predict the product of the Pinacol rearrangement at the bottom. We don't have methyl groups here. We have these, instead of the methyls, these carbons attached to the alcohol groups are parts of ring systems. Okay, all right, so let's look at what we get from this Pinacol rearrangement right here. So notice how the methyl group migrates to the carbon adjacent to it. So a similar thing is going to happen here. Ultimately, that carbon is going to end up right there. Okay, and what you're going to see here is that we, instead of having two 6-membered rings, we're going to have a 6-membered ring and a 7-membered ring. All right, so this is the product right here. Okay, I guess I got it backwards because we're going to move this one, but it's a symmetrical molecule, so it doesn't really make a difference. So what happens here is we are going to make the carbocation. All right, so let me just draw that important intermediate right there. Okay, all right. Okay, that's what we do. We make that protonated alcohol. We lose the water to make this carbocation. Then one of our alkyl groups migrates over to the new carbocation to generate this oxonium ion, and we lose the extra proton to produce the product. Okay, all right. Let's look at a synthesis problem. How do we make this compound from this alcohol here? What you recognize here, of course, is that we've added some carbons. We have 3 extra carbons in our molecule. We have been relying upon the Grignard reaction to produce compounds like this before, but right away you kind of see a problem that these new carbons that we've introduced have alcohol groups on them. Therefore, they could not be part of a Grignard reagent. But one thing to note here is that this is a 1,2 diol, easily obtained from the alkene, right? So that's a group that is perfectly compatible with the Grignard reaction. So let's do that as our last step. We're just going to take this alcohol and treat it with osmium tetroxide. Okay? All right. So now this problem becomes a little bit more manageable. It looks like what we're basically doing is adding a methyl group and an allyl group to that carbon right there. All right, and we know how we can add Grignard reagents to ketones to do that. All right, so let's just imagine we're going to add the allyl group last, and that's pretty easily doable by just adding it to this ketone. How do we add the methyl group? Okay. All right, so we can't really add it right to an alcohol, so we have to think about a legitimate precursor, and one of the ways we could do this is we could just take the methyl alcohol and treat it with PCC, and right away you see kind of a stronger relationship to our starting material. This methyl group, of course, we're going to introduce this by just adding it to an aldehyde. Okay, so that's the aldehyde we need, and hopefully everyone sees a very easy reaction that would do this conversion. Just treat this with PCC. All right, let's label these steps A, B, C, D, and E. All right, so there's another correct answer. I guess we could say it would be okay to reverse steps B and D, right? Because we could add the allyl group first and then add the methyl group. We'll look at a reason perhaps in a couple of chapters where that's not quite as good because of the types of ketones that we generate, but for now it would have been okay to reverse steps B and D. All right, so this is a way to do that. Okay, and it takes advantage of the unique ways that we can make a 1,2 diol. All right, let's look at another topic here. There's chemistry is not the only way to accomplish an oxidation of an alcohol or a reduction of a carbonyl group. This happens in biological systems all the time. Okay, so one that you might be personally familiar with is ethanol, which has to be metabolized, and basically what happens is it goes through a series of oxidations, ethanol to acetaldehyde to acetic acid, and eventually to carbon dioxide. Okay, all right, so what does nature do to how does nature accomplish these reactions? We already talked about how chromium-6 was not compatible with biological systems. Sodium borohydride isn't either. Okay, all right. So instead of using sodium borohydride and chromium-6, biological systems will use much milder reducing and oxidizing agents in the presence of an enzyme, okay? So the universal biological reducing agent, often I think called a cofactor, is this molecule here, nicotinic acid dinucleotide hydrate, or the reduced form of that. And we're just going to abbreviate it this way because this is the part of the reagent that actually is doing the reducing. Okay, the oxidizing form here is called NAD+, and we're just going to represent it this way. Okay, so this is a hydride donor. This is a hydride acceptor. All right, so what happens here is that nothing happens unless an enzyme complexes to the carbonyl group or the alcohol group and gets the reaction started. So let's look at alcohol dehydrogenase. Okay, So we're going to form some sort of complex. We'll call this is the enzyme alcohol dehydrogenase. It's the enzyme that's responsible for the metabolism of ethanol. Okay, so what happens here is that a complex with the enzyme forms, and this activates this system to transfer its hydride to NAD+, and this becomes NADH, and in the process, our CO single bond becomes a CO double bond. Okay, the beauty of this reaction here is that it's reversible. You could just take NADH and turn the aldehyde back into the alcohol, and what determines the direction the reactions go in is the presence or absence of the enzyme, and oftentimes whether you have oxygen present or other things as well. Okay, all right, so in biology we use much milder reagents that aren't capable of doing the reduction in the absence of the enzyme, so that's a very special case. You may say, all right, I have a lot of ethanol in my system. I have a job interview in an hour. Could I just drink a little bit of chromium trioxide to get the process going a little faster? Well, you can't. That wouldn't work. For one thing, chromium-6 is quite toxic, but even more important, a biological system as complex as a human is just loaded with OH groups. So every one of those could potentially do the oxidation with chromium-6, whereas alcohol dehydrogenase will only make a complex with ethanol, and so only ethanol gets reduced under these conditions. Okay. Conversely, you may say, okay, I'm wasted and I want to stay that way. Could I just drink some sodium borohydride to maintain my state of bliss? Again, no, you couldn't, because every ketone and aldehyde in your system would be reduced by sodium borohydride, whereas only select ketones and aldehydes like acetaldehyde could participate in that process in a biological system which required the enzyme, the cofactor, and the substrate to all be there together. Okay, so systems are much more selective. But notice an important relationship here between a biological system and a chemical system. The arrow pushing is kind of the same, okay? We're removing a hydrogen as H minus in this case, and if we wanted to add it, we would add it as H minus, just like when we added sodium borohydride to a carbonyl group. Okay, all right, let's look briefly at the chemistry of sulfur analogs of alcohols. These are thiols. All right, so there's a few differences between ROH and RSH. One is that this group is not associated with hydrogen bonding. Okay. All right, so let's look at boiling points of things that have of an alcohol and a diol that have basically very similar molecular weights, ethane diol and N-propyl alcohol. What we see here is that N-propyl alcohol, because it engages in hydrogen bonding, has a much higher boiling point. Okay, than the corresponding sulfur compound. If we look at the compound with the same number of carbons, we see even though the ethanol has a much lower boiling point, much lower molecular weight, its boiling point is much higher. And again, this is due to the hydrogen bonding. All right, another big difference is the pKa. The diols are much more acidic. The pKa of ethane thiol is about 11. Whereas ethanol is very similar to water at 16. Okay, and the reason for this enhanced acidity is the fact that our negative charge is spread out over a much larger area than it is here. Even though oxygen is more electronegative, the fact that sulfur is a much bigger atom and more polarizable means that the anion is delocalized over a much larger volume, and the anion from deprotonating the thiol was much more stable than the anion from deprotonating the alcohol. Okay, all right, so that results in a much more acidic compound. All right, so because the pKa here is 11, much lower than water, we can use KOH as a perfectly adequate base for making the thiolate anion. Okay, this reaction here will essentially go completely to the right. So KOH or NaOET or something like that are perfectly acceptable bases for removing the hydrogen from a thiol. Okay, another fundamental property of thiols: they stink. Okay, they're the most foul-smelling compounds you can imagine. Okay. Let's see, rotten eggs, or that smell is due to hydrogen sulfide. So humans have the ability with their nose to detect very small amounts of thiol molecules. Okay? All right, so that's another fundamental property. Natural gas, CH4, or methane, it doesn't really have a smell. So what they do is they deliberately add a very small amount of a compound called T-butyl thiol, and that's what gives the gas its smell. Okay, so you wouldn't be able to detect it until very large amounts built up if it wasn't for the presence of the trace amount of thiol that they put in there so that you can detect it. Okay, all right. Oxidation is a very interesting reaction of thiols. They don't oxidize the way alcohols do. You don't make the sulfur analog of an aldehyde with most oxidants. Okay, when you oxidize a thiol, the compound most oxidants produce is a disulfide, where you just make a sulfur-sulfur bond. You just take two of these together and replace the SH bonds with an SS bond. All right, so oxygen and iron is a very efficient reagent for transforming two thiol units to a disulfide. Okay, you can transform a disulfide back into a thiol by treating it with a reducing agent like sodium borohydride. Okay, so thiols are very important molecules in proteins because one of the common amino acids is cysteine, which has an SH group. And under oxidizing conditions, you can actually form a linkage between two remote cysteine residues. So you have a ring here where you didn't have one before, and this has a big effect on protein structure. This type of structure in a protein is referred to as a disulfide bridge. Okay, all right, so the last thing we're going to talk about is spectroscopy. We covered a lot of this when we talked about spectroscopy, but let's just reinforce a couple of things. The OH band is the most characteristic thing that we'll see in an alcohol. It occurs in this range here, and it's intense and broad. Hydrogen bonding will decrease the frequency to about 3,300, and it's also going to increase the intensity. So we see a little bit of a shift in the OH stretch depending on the concentration, which affects, of course, how much hydrogen bonding we would have in the system. Okay, in the proton NMR, you might think, let's look for the OH peak, but that's not a really good way to analyze an alcohol because this peak is usually broad and it's not coupled to the remainder of the spectrum, and it comes in a very broad area, 1 to 5 ppm. And it's likely that every time you make a sample of even the same compound and take its NMR spectrum, you'll see it come at a different place. This is because this peak is very concentration dependent. All right. The OH peaks in carboxylic acids and phenols actually comes at a higher value, and we'll discuss those later. Okay, the other distinctive feature of an alcohol, this is a little bit more reliable, is that the hydrogen that's on the same carbon as the oxygen is going to be in kind of a much higher region at 3 to 4.5 ppm, and tertiary alcohols, of course, don't have a hydrogen there, so they would lack this peak. Okay, in the C13 NMR, the most distinctive feature is of course, this carbon right here, because oxygen is electronegative. We see this peak come at 50 to 80 ppm. In mass spectrometry, alcohols are kind of difficult in a lot of cases because the water loss from an alcohol is often so quick that sometimes you don't see apparent ions. So special techniques usually have to be used to observe apparent ion in the mass spectrum of an alcohol. All right. Okay, so let's just look at the spectrum of an alcohol, and then in the next case we're going to do an unknown. So this is phenethyl alcohol right here. Here's its infrared spectrum. Okay, distinctive features that you see are this, which is the OH. These are our CHs. Notice that we probably expect a carbon-oxygen stretch, but where? Is it there? 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 Who knows? Okay. It's not a very distinctive band that you can spot. Okay, so you don't want to even look for that one. It's not a reliable feature of in the NMR or in the infrared spectra of alcohols. It's very hard to spot the CO stretch, CO single bond stretch. All right, let's look at now the proton NMR. Most of the time what you're going to see is that the OH proton is not coupled to the rest of the spectrum. Okay, so this is the OH group right here, and it's occurring as a singlet, even though the spacing between here and here is only 3 bonds. We don't really see the coupling, and this is because the hydrogen is being exchanged rapidly due to the hydrogen bonding interaction. All right, we see that one of the CH2 groups, which is a triplet, has a higher chemical shift than the other. This is, of course, the CH2 right there. That one's higher because they're on the same carbons as an oxygen. Okay, in the C13 NMR, we can make out a unique peak right there that we can attribute to the CH2OH group. All of these are the sp2 carbons. These are the sp3 carbons, and this one is higher due to the electronegative oxygen atom. Okay, and finally, let's just go through a spectroscopy problem. We're going to suggest a unique structure that has the formula C6H14O and has the following spectral data. All right, so what we should do here is we should take this formula, calculate the degrees of unsaturation, and you find that there are no rings or double bonds in this compound. This is because if we look at the relationship here, CnH2n plus 2, 14 is the maximum number of hydrogens per carbon that you can have when you have 6 carbons. Okay, so this is a perfectly saturated compound. So we're not going to look for any compound that has any sort of unsaturation in it. All right, it's a saturated compound with an oxygen. This means that only two functional groups are possible, alcohol or an ether. And what we see right here is an obvious OH stretch, so we're not going to consider ethers as structural possibilities. Okay? All right. This molecule has some symmetry because note that we have 6 carbons, but only 4 peaks. So there's going to be some degree of symmetry in our molecule. All right, so it's 2 hydrogens, a doublet. This chemical shift suggests that this is, in fact, our CH2 group. The fact that it's a doublet means that there's 1 hydrogen on the adjacent carbon. So there's a CH there. Okay, if you look, there's only 4 more carbons in this compound. There's 6 carbons. Here's 2 of them right here. We know that there's symmetry. So this is the only way we can really make this compound work. Let me draw a better 3 right there. This is the structure of our compound. Okay, so we have a triplet, 6 hydrogens. Each of these CH3 groups is a triplet, and when you add 2 of them together, you get 6 hydrogens. Each of these CH2 groups should be, well, actually they're overlapping. All 5 of these hydrogens overlap, so there's not really much definition there. That ends up being a multiplet, but this is the only structure that works. Okay, all right, so we can really solve it by looking at the C13 to see that there's some symmetry, and we can find the hydrogens that are on the same carbon as oxygen in the proton NMR spectrum, and we're kind of limited because of the requirement to have a symmetrical molecule, how we can distribute the other 4 carbons. Okay, all right, so this is where I think this is the last video in this chapter, so I'm going to end it right